So we have discussed about the photosensitization process. So now for olefins, this is a very important concept. So now we'll go for the photochemistry of conjugated olefins. So we know that when we have a 1,3-butadiene, this can also exist as a in the cis form. Okay. So here when we have C1, C2, C3, C4, if we can rotate C2 and C3, when we have CH2 double bond like this. So here if you rotate C2 and C3, we will get trans plus cis. Okay, so at ground state, if you see at ground state, it is a thermal conversion. We can call it as a thermal isomerization at a ground state. At a ground state, this is a thermal isomerization. So 95% of trans will exist. 1,3-butadiene will exist at 95% of trans at a ground state. Only 5% will be the cis. So when we will go for the excited state, here we have only trans. There is no cis, because the energy barrier between C2 and C3, it's very high in case of 1,3-butadiene. So for this, photochemical energy is not sufficient to rotate this C2 and C3. Photochemical energy is not sufficient. Only thermal energy is sufficient. So that's why at ground state we are seeing cis and trans in a 95:5%, whereas in a photochemical condition, that means in excited state, we will see only the trans but not cis. And we'll see the reactions of 1,3-butadiene in the presence of direct irradiation and in the presence of photosensitization. Photosensitization means we are generating the intersystem crossing artificially. So when we have 1,3-butadiene in the direct process, we will get 3 products. This is the one product, this is another product, 10% of dimer of this in the direct irradiation. And when we have a triplet sensitizer, when we use the triplet sensitizer, in that case we get 3 products, and these are the 3 products we will get when we use the triplet sensitizer. Okay, so we'll see the mechanism for all 3. This is also photochemical light and this is also photochemical light. Okay, and what is the mechanism for this? This mechanism is very simple. Like when we have this kind of conformation, we'll get cyclobutane derivatives, whereas this one exclusively comes from the trans isomer. This goes here and this goes here, so that we will get this form. Okay, so this one we can see this one how it comes. So when we have a 2 moles of trans form, so this is going this way and this is going this way, so that we are getting this. And this one is coming from, one is trans, sorry, both are trans only, position is different, and this is going like this and this is coming like this, so we are getting this compound. And for this the mechanism is different. This can be like I think so. This is the mechanism for this. Okay, so when we are using a direct irradiation, in that case we are getting a cyclobutane derivatives and this bicyclic compound. So when we are using triplet sensitizer, that time we are getting a different products. So this is why photosensitization is very important in a olefin compounds. Actually, this is not the actual mechanism. It's not the actual mechanism. It's too lengthy. Okay, I will draw the mechanism for this. This gets homolytic cleavage. So one will be at a triplet state, another one will be at a ground state. Okay, and here double bonds will be there, and if these two combines, then we have this. Okay, if these two also combines, so we'll get a this product. Okay, after this, like this, now if you take this homolytic cleavage, and here we have radical. Now if imagine that these two form a bond, now give the numbering 1 2 3 4 5 6, and these two form a bond, so that we'll get this compound. So we have one important reaction in examination point of view. It's very important. So this reaction is called as a dipyromethane rearrangement. So this is very important. So we'll see the mechanism for this. So just give numbering so that it will be very easy. If you don't give numbering, it will be very confusing. So just first we'll do the homolytic cleavage of this one. So this reaction can goes in a N2 pi star singlet state as well as N2 pi star triplet state, and all kinds of 1,4-dienes are undergoes this reaction. Okay, so the first step is breaking of both the double bonds will break, and the next step is bond formation between C2 and C4 carbon, so that it gives the cyclopropane derivative. And third step is, after forming cyclopropane derivatives, we have to break one bond. It can be C2C3 or C3C4. It depends. How it depends? If aromatic character is there in a starting precursor, that we have to regenerate it. So if you break C2C3, if aromaticity is not generating, that means you cannot do that. We have to go for C3C4. If you are breaking C3C4, their aromaticity is not coming, means then you have to go for C2C3. And also it depends upon the electron rich group should be part of the ring system, and electron withdrawing group should be part of a double bond. Okay, now we'll go for the second step. This is 1 2 3 4 5. So next step is the formation of a bond between C2 and C4. This bond, this is the S1 state. Now 1 2 3 4 5. So there are two possibilities now. First we will break C2 C3 and here C3 C4. If you break this bond 1 2 4 5 3, so here radical is there, here radical is there, and here radical is there. So where adjacent radicals are there, they form a double bond. So these two radicals form a double bond, and this one combines with this C5 carbon, and it leads to form this product. So now we'll go for C3C4. Since C3C4 we are breaking this one, that means this is radical, this is also radical, and then this is radical, here radical. So these two form a bond, and these two combines together, and it forms a this. So when we have a C2C3 cleavage, in that case the double bond the double bond which is present at C1 C2, that is retained. When we break C3 C4, now this double bond was there, but this double bond is not there. Okay, so for symmetric dienes it's not matter, like it can be both the mixture you will get, because here no regional selectivity. So when we have this kind of compound, so this is also 1,4 diene. So now we'll break this one. Now we have radical here and also radical here. So this is 1 2 3 4 5. In the next step we have a C2C4 bonding. These two form a bond. We have it like this. Now C2 C3 C4 C5. Now we will see C2 C3 breakage and C3 C4 breakage. Now you will get clear idea. So now we are breaking this. So after breaking this you broke, so C3 comes here, C4 C5 will be here, and here radical will be there. And when you see this one, so here we are breaking a C3 C4, that means here radical comes, double bond, and here the product will be these two form a bond, and these two form a double bond, and this one forms a cyclopropane ring, and here we will get this product. Now which one is the major one? So this is the major. I can say this is 100%, this is 0%, because Cu2 C3 cleavage is reproducing the aromaticity. Initially this is aromatic, now C2 C3 produces the aromaticity, whereas C3 C4 is not producing aromaticity here. So that's why C3 C4 is completely ruled out. Okay, so this one we have done. Now we'll go for this condition where we have electron releasing group that should be part of ring system, where we have electron withdrawing group that should be a part of double bond. We have pH here, and here we have two methyl groups. So here also same procedure. Now 1 2 3 4 5 C2C4 forms a bond here. One, 2, 3, 4, 5. Now here two possibilities are there. C2C3 break, C3C4 break. If C2C3 got break, so C3 comes here and this is free radicals, and if C3C4 got break, C3 comes here and here this one. So now these two form a double bond here, and this forms a cyclopropane ring, and here these two form a ring here, this one. So now which from here we can predict whether C2C3 is a major or C3C4 cleavage is major. So as I said that electron releasing group should be a part of a ring, and electron donating group, so withdrawing group should be part of a double bond. So here the phenyl is more electron donating capacity compared to methyl, this we know that. So here phenyl group should be a part of the ring and methyl group should be a part of double bond. So C3C4 cleavage is major here. So this is not possible, because in this case electron donating group is a part of double bond, whereas electron withdrawing group is part of the ring. So that is not possible. So because of that C3C4 cleavage is major here. And there are some examples I am not going to draw the mechanism for this, just so now it can be either 1 4 means 1 2 3 4 5 1 2 1 2 3 4 5. So it can be this or this. So here the mechanism, the final product I am writing here. The same procedure, you just follow the same procedure, you will get the mechanism, you will get the product. This is in the presence of triplet sensitizer. If you use the triplet sensitizer, then only dimethyl rearrangement you will see here. If you do the direct sensitizer method, in that case you will get a cyclooctane. This one you will get. Okay. So next I think we can draw this also. So 1 2 3 4. So the product will be this is the product. Okay. pH, Cn. So here also reaction selectivity will come into the picture. So the electron this is electron releasing group. This should be part of ring and this should be part of a double bond. Similarly, anything electron releasing group. So this is about the dipi methane rearrangement, and one more is the oxo dipi methane rearrangement. So this is also same, oxo dipi methane rearrangement. So in this case, instead of carbon, we have a carbonyl compound, and here the product will be the aldehydes. Just see, this is also same. Radical comes first, then C2C4 bond forms, and here the cleavage is only one cleavage, that is C2C3, because we have to regenerate this carbonyl compound character. So we cannot do a C2C3 cleavage. Only possible here is C3C4 cleavage. So now these two form a ring. This is the first. Here no reaction selectivity, nothing. Okay, because no possibility for reaction selectivity also, because in one side we have oxygen. So whatever the substituent here, we have to break C3C4 bond, then only we can generate the carbonyl character back. So this is about the oxo dipi methane rearrangement. And one more cycloadditions of olefins. So when we have a diene plus this one olefin, so here we will get a 3 products. So 1,2 product, 1,3 product, 1,4 product. 1,2 product is means ortho product, like this, and 1,4 product means para product, and 1,3 product means meta. This is not actual process. I will draw the mechanism for 1,3, so that from there it will be clear. So this is actual hydrocarbon benzene. Okay, so first 1,3 process. For 1,3 process, this is a direct mechanism, and for 1,4 process, we'll break all 3 bonds. So now these two form a bond and these two form a bond, so that we'll get a para product. And for meta product, we'll break these two. So this is 1,3, 1, 2, 3. These two should form bond, right? So this one and this one, and these two form a this kind of bond. So here ring contraction takes place in meta addition. So this is the product you will get for meta product. Okay, this is about the cycloaddition for this one. And another thing, one rule here. So where the substitution is there, imagine the substitution is here, the ring form also should takes place from here only. If it is ortho product, so this should be the product. If it is meta product, then this should be the 1 2 3 4 5 6 1 2 3 4 1 2 3 4 5 6 there is 2 and 4, so this should be the product. Just remember, in the meta product there is a formation of cyclopropane at C2 and C4. Just give the numbering, it will be very clear. For meta it will be para it will be 1 2 3 4. This should be a product, so like that. So this is about this one, and I have some more reactions about this conjugated ions. I'll make one more video, just 3 more reactions, so that this conjugated olefin also get over.